Hello, everyone. Good morning. So we are back for the second day of the school. We have again Professor Torres, Dr. Torres, not professor yet. Uh, so we can start. You guys can send questions in the link in the Google Meet or in the chat on YouTube. Don't be afraid or shy. Questions are really welcome, right, Maurício? And patient makes the school really better. So enjoy the lecture. Good lecture, Maurício. You.
Welcome again to the set of lectures related to either physics, specifically related to simulations, Monte Carlo event generators. As to say, my name is Johan Maurício Torres, and any question you can send again in this email that appear here. So we start with this lecture, that is lecture number 2. In that, we are going to talk about some introduction related to numerical integration. Very, very important and fundamental for the study related to collider physics from a simulation point of view. And as is usual in colliders talks, so colliders lectures, is necessary to understand from a theoretical point of view the standard model of particle physics and beyond the standard model. So, as say in the lecture 1, my work is related to computational physics, but in this case, we apply computational particle physics technique to collider physics. And this is the content of the lecture today morning. In that, I separate in 3 parts. First part is related to numerical integration, but in case we are going to use Python to show how some of the most important numerical integration methods works, like trapezoidal, like Simpson rule, like Riemann sum, and the most important numerical integration that the Monte Carlo event generators uses, that is the Monte Carlo method. Here, after that, we are going to do a review from a theoretical point of view, the standard model and beyond the standard, because this is very important to do accurate simulations. We need to understand what the Lagrangian means, how we can interpret the Lagrangians, and we need to do that because I do here a comment that say important to Feynman rules package. Feynman rules package is a software that works inside of mathematical Wolfram that use the language of Wolfram programming. So it's necessary to understand the Lagrangians, the properties of the Lagrangians, the properties of the interactions, with the objective to do accurate implementation of the Lagrangians package. So we start with the first topic, that is numerical integration. We know that numerical integration are a set of mathematical methods that we use to solve that case integrals, but in a approximation way. So we are going to use numerical mathematical method solving the definition of an integral, that is the area under the curve. So we are going, our objective here to obtain the area under the curve using smaller sections of the area and sum each one of this area and obtain in an approximation way the result, that is depending on some parameters are very, very exact. So our expression that we are going to solve a very popular expression that we find in the standard model, that is the scalar potential of mechanism. But in this case, we don't talk physics related to that. We are going only to see from a mathematical point of view that this is a function, and we are going to solve the area under that curve using different numerical integration method. And we start here with the Python code. So we have here our function, that is the Higgs potential, and the Higgs potential has that form. This is a typical potential that we find in quantum physics books and particle physics books. That potential, our objective here is find the area under that curve. So we start here, for example. First of all, find the solution, the exact solution. Right? Remember, plus. Here is a good zoom. So this is the potential, right? The Higgs potential. And our objective, as I say, is calculating the area under the curve integral using. So the first step is obviously obtain the exact solution of that numerical, sorry, that function, and the result is that number, between this interval and this is the exact solution, the exact area under the. And now we are going to use different numerical integration methods to do the same things, but in an approximation. So after of that, we need to define what means trapezoidal method. The trapezoidal method works using the function and separate using trapezoids. So the main objective of this method is sum the area of each one of these trapezoids, and with that strategy find the area under the curve. For example, we have this function calculate. this, for example, we can use different trapezoids to calculate the area under the curve. If we calculated this area for only only two trapezoids that are the left and right trapezoid, obviously the approximation is different from that solution. So we need to increment this the number of trapezoids, and the approximation is better if we use a larger quantity of trapezoid. So for example, we use here a quantity of 20 trapezoids, and we obtain this is the exact result so we can see that the approximation is very good. So this is the trapezoidal method that use trapezoids, and we find the area of each one of the trapezoid to find the area of function. Exists another method that we call Simpson method. That we have here the definition of the Simpson method. The Simpson method works in a different form because Simpson method use inside of the algorithm use interpolation. So we can obtain a formula via the interpolation to find the method that use again a separation of the area in different parts using that curve that at the final counts are parabolas. So we find the area of this each one of this parabola and find the approximation solution. So this is the method, the Simpson method, and works. For example, this is the method, and we can see that, for example, for only two points that we are going to interpolate, we can increment, for example, for 34, and the function is very good. No, we can increment the numbers of points of the interpolation, and we can obtain a result near of the exact solution. In here the same thing, and we can see that if we use, for example, that number of the number of the interpolations, we can find a result very near of the exact solution. So that is the Simpson rule. Okay, and exists another method that when we study numerical integral calculus, the first topic that we learn is the Riemann sum. That is approximation of the integral. We know that we use that to define that term in mathematical, that is integration. So Riemann sum we can use as a numerical method, and here we have the definition of the sum and room. That is we are going to dividing the area using rectangles. So the strategy is sum the area of each one of these rectangles that are under the curve, and we can approximate the solution of that integral. So we can see here, for example, the solution for a set of number of rectangles, for example, the bat animation. But if we increment number of rectangles, we can obtain in an approximation a better result that is near again of the exact solution. So the algorithm sum each one of these area of this rectangle, and we obtain an approximation solution. And finally, we have the best method related to the event generators. That is the Monte Carlo. So the Monte Carlo the Monte Carlo method works with a set of random numbers. So the strategy is put numbers from a randomly sample. So we are going to see with Python. And for example, here, this is the Monte Carlo event. For example, we can start with only 10 numbers that are that the distribution is randomly. Okay, we have points outside of the curve and inside of the curve. So the area, obviously, we are going to count only the points that are inside of the area. If we take the number of the points inside of the area and we do the division between the total number of random numbers, we can obtain in an approximation the area on the I why the points? Uh, why background? The white or the black? So if we only have the numbers, we have numbers that are outside of the curve and inside of the curve. And obviously, if we increment each one of the numbers, random numbers, we have numbers that are outside and side of the curve. So we can sum all the points that are inside of the curve, and we do the calculation of division between the total random numbers, and we can obtain in an approximation the area under the curve. So we use that strategy to solve any integral. See, yes, this is only we take only the numbers that we count the numbers that are inside under the curve, and we take that number and we do the division between the total random numbers, and that is the area. Oh, random numbers in that space, in that space between the integral intervals. Yes. Okay. The question is basically how Monte Carlo works. Monte Carlo works. We we have, for example, in this case, we have 100,000 points, random points, and we put with a probabilistic distribution in a rectangle around of the function. So we can points outside of the curve, inside of the curve, that is totally randomly. And the strategy is only count the numbers that are inside of the curve, and that number that obviously is a number smaller than the total number, the total random numbers. In this case is 100,000. So we sum all the numbers that are inside of the under the curve, and we do the calculation of the division between that total number. So the area is that. The area is only the total numbers over the total numbers. Total numbers that are inside of the area over the total random numbers. Okay? And the result is an approximation to the area. So that method is used by the Monte Carlo event generators, because we are going to see in another lectures that the function is different from that. The function that we are going to solve a very, very difficult integral that we call quantum chromodynamics master formula. That depends on infinite parameters, basically. So we are going to see in another lecture. Okay, so that is the definition of numerical integration. Okay, so we are going to pass to another but necessary topic, that is a review of the standard model. So we know that at the beginning of the 20th century exist basically types of physics. Physics that study the small scales, and physics that study the large scale. So in that case, we have the non-relativistic quantum mechanics and the general relativity. So obviously, quantum mechanics study the physics of the small scales, and the general relativistic study the cosmological scale. But exists another problems that two types of physics don't explain. That, for example, is insufficient to explain some phenomena like relativistic bound states, inelastic or transmutation particles, decay of composite or elementary particles, and the vacuum energy. That problems, for example, are not solved in exact solution by these two theories, non-relativistic quantum mechanics, the general relativity. And what is the solution? So we have a set of problems here in red. Have a set of problems that physics don't solve, but the physicists created a very general theory that is most powerful that the relativistic quantum mechanics and the non-relativistic quantum mechanics, that is quantum theory. And if we take the quantum field theory and use some topics related to group theory, topic theory, we can obtain standard model of particle physics. That model solves the problems that in that time are unsolved. So the standard model of particle physics is basically sum equation. The sum between the quantum field theory and group theory. It can obtain the standard model of particle. The standard model of particle physics need to be some properties to reproduce the phenomenon related to elementary particles. For example, using the group theory, we know that there exists a symmetry group that can explain that problems and do some predictions that after of the years was confirmed. For example, that group is the electroweak group SU12U1, and that group is inside of the standard model, and all the Lagrangians that we can write is the requirement to respect that symmetry. So with that symmetry, with the diagonal generators of that symmetry, that group theory, we can obtain that equation that is a with charge operator, we can write the particle count. We are going to see that the fermion count. So we know that the standard model can be a difficult theory to understand, but we can separate the Lagrangian standard model SM in different sectors: fermion sector, gauge sector, scalar sector, and Yukawa. Fermion sector obviously study all the interactions of the fermions with the symmetry bosons of the theory. The gauge bosons only study the symmetry bosons of the theory, and the scalar sector study the most simple cases in that we have only one scalar interact between itself and gauge bosons, and we need the interactions between our fermions with the scalars that is given by the Yukawa sector. So we are going to present each one of these sectors. But here again is the same comment. Each one of these tangents are invariant under this symmetry group SU12, U1Y. Here don't appear the group of these strong interactions SU3C color. So exists that symmetry that the Lagrangians need to be respect. Okay, and we start with the fermion content. Using the charge operator, we can write content. We need to have inside of the fermion content all the particles that we see in the experiment. Important. For example, we know that we see neutrinos that are neutral leptons that appear in the first component of that vector L nu A, and we have the charged leptons in the second element of that vector L. A is equal to 1, 2, 3. So we have the active neutrinos that we see in the interactions, in the weak interaction, and we have the L, that electron, mu, and tau. And for the neutrinos, we have the electron neutrino, mu neutrino, and tau neutrino. And that numbers, we can interpret it as, for example, if we want 1, that means that each one of the fields don't interact with the strong interaction. We say that are singlet. When we have the number 2 or a number different from 1, 2, we say that fields interact as a doublet with the bosons as well group. And the -1, the third number, means that each one of these fields has as a value hypercharge equal to -1. That is interpreted. That is the interpretation of that number. Not that number here say how these particles transform under the group of. So, for example, we have here the here appear L, because that fields that appear here are left-handed fermions, left-handed leptons, and are here we have the right-handed part charged leptons, and again are singlet on the SU3 group. That means that leptons don't interact uh, with the strong interactions and don't interact with the S12 gauge group. Are singlet, right-handed part of the charged lepton, and has -2 of hypercharge. And we can see that we don't have a right-handed neutrinos in that fermion content that we are going to explain in final of these lectures. But this is the content related sector. And here we have the quark sector. Quark sector are made of quarks, obviously, and we have 3 types of up quarks and 3 types of down quarks. We have in up quarks, up type quarks, we have the up. I need to up, charm, and top are the up type quarks, and in the down quarks we have down quark, trench quark, and bottom quark. Are again this is the left-handed part of quarks, and this is the form that is different from this number because quarks interact with the strong interaction. So that quarks has transformed as a triplet. Here appear number 3. Interact with the strong focus, with a strong interaction, and our doublet group because that fields interact with the 3 gauge symmetry bosons group and has 1/3 hypercharge. Again, we have the right-handed part of each one of the quarks, and again are triplet, singlet, and has in this case 4/3 as a hypercharge value. The interpretation is the case down type quarks. So this is the fermion content, and the physics that describe the fermion content is given by the fermion sector, that is first term of tangent. The fermion sector say how if fermions that was presented in the slide interact with the bosons. So that interaction is given by that Lagrangian. D have here for example L that is that vector of component interact with the gauge bosons via D. Here appear the 3 symmetric bosons W, W1, W2, and W3. And we have B, that is the boson related to the abelian 1Y that in the group. So if we replace that covariant derivative, that we obtain terms in that appear L and each one of gauge symmetry bosons. We have 2 different D because we have a D for the fermions that interact that are doublets group, and we don't have the W boson here because that only to the right-handed part of fermions are singlet on the well group. So when a field is singlet, don't interact with that bosons. So this is the fermion content. I know that it's some difficult to understand that, but it's very, very important to understand because I put that comment beginning of the lecture. We need to understand and interpret the Lagrangians because we need to implement the Lagrangians inside of the package. Important to understand. We have here the fermion content after of replace and do some another calculus like substitutions or diagonalization to pass from a non-diagonal basis to a diagonal basis. We can obtain the Lagrangians, the physical Lagrangians. Here appear the W that we can find in experiment. And we have here A that is photon. And we have Z that is the boson. And you can see that W, A, and Z interact with that J. J means current. When we have that particle, W plus or minus a charge, electric charge particle. So we call that Lagrangian, the Lagrangian that describes the charge current. Because we have a boson, electric charge boson. And we are going to present what means that J, but J is related to leptons and quarks. In that case, photon and the Z boson are neutral particles. So we call that Lagrangian neutral current Lagrangian for the fermions. So J appear here. For example, have that J. J the charge current of the lepton that interact, you can see here. JWL appear here. JWL. So W interact with that current. W interact with leptons and the correspond lepton neutrino of that lepton. So of this charge current in the side of the charge boson W, and we have the neutral current D here for the leptons, for the quarks, and we have here the photon interact with the fermions. This is the electromagnetic interaction. So each one of the constant variables that here are parameters of the model. Have GFV, GFA, and have here that number, and here appear an important concept that is parameter. All the models that we use in particle parameters. Parameters is a quantity that can be measured by experiment or predict by a theory. By at a final accounts, we a parameter that we need to measure. So we have W in that case, a W that is the Weinberg angle we measure in experiments. So that are numbers that we can implement in fine rules. So with the fermion sector, and we need to explain the gauge sector. The sector, as I say, only related to the bosons of this standard model. So we expect to obtain interactions or only with bosons. So we have these two types of Lagrangian that this is the form we need to write that in that form because that form is invariant. That group that I show at so this is the Lagrangian of the bosons. And again, if we make substitution and we do a transformation of a non-diagonal basis, we can obtain that Lagrangian. The physical bosons, and we need to understand that Lagrangian and interpret it correctly. For example, we have here that term, for example, have 4Ws. 4Ws implies, for example, we have here and that means after of do some steps, the interpretation is basically the interaction the Feynman diagram between 4W bosons. So the standard model says that interactions 4W bosons. We can measure that in particle experiments. So the Lagrangians are not only mathematical formulas. We can interpret it from a physical point of view. So it's important to understand that. For example, we have here, I am going to here and here I write that that's Lagrangian. That so the interpretation via Feynman diagrams basically interactions between two bosons. Boson. So the standard model of particle physics say that we can measure that particle experiment. So that is obviously very general interpretation of the Lagrangian. Obviously, things that is necessary to understand, like obtain the Feynman rule, Lagrangians, etc. That is a very general form to understand one of the terms of the Lagrangians in general. So this is the gauge Lagrangian. So in the scalar sector, we obviously appear famous boson. So this is the Lagrangian of the Higgs boson. We have P that is Higgs field. It's not the, it's the field. And for me, the scalar sector is one of the most difficult things that understand. So my work here is don't explain how mechanism and geometry works. Was another lecture, very difficult, but I am going only to show the result that here. Here, for example, we have interactions between two or a quantity that one of the objectives measure lambda. Important to how for example here interactions two W's boson have mass term. Mass term are terms that we have only two fields. For example, we have here H boson, only two boson where that means that the term. So after of the spontaneous symmetry breaking of continuous symmetry that mechanism can obtain mass for the Higgs boson and for the bosons W and the photon appear here massless. So this is sector, sorry, the scalar sector, and this is the result of this. And the final thing that we need to understand the Yukawa sector, because we need we can think that we need interactions fermions and because that was a particle that was in the scalar sector. So we need that interaction. And that interactions is given by the Yukawa sector. That's why are the strength of interactions, our metrics. And we have here, for example, interactions between the leptons, right-handed part of the with the Higgs field that was introduced in this sector. We have here the quarks, quark down type, and the left part of the quarks filled again with the up type quarks, but we can see because we don't have say at the don't have right hand minus, so we don't have terms our sector for neutrinos. That means standard model that here appear the mass. That means that neutrinos inside of the standard model neutrinos are massless particles, but that is true. So we can see that standard model is a theory that need to be extended. We don't standard model a priori say that neutrinos are don't have mass, but another phenomenon that neutrino oscillations that depends on mass that particles. So we have a contradiction, experiment and the theory. So that say that we need to extend this first proof that the standard model needs to be extended. Here we have the result of that Lagrangian that have here mass for the large leptons, mass for up-type quarks, mass for down-type quarks, and we have the interactions between the Higgs and each one of the leptons. You can see that the interactions between Higgs and the leptons depends on the mass of the particle. So if we have a heavy lepton, implies that the interactions with the Higgs boson is strong. So we finish here with that term that represent the interaction. All Lagrangians, a form to understand all that equations. For example, photon. Photon is a particle that only that particle that have charge. For example, we have a line that connect leptons. We have a line that connect the W boson charge. We don't have a line that connect with neutrinos because are electric parts. particles, totally neutral particles. And we have, for example, a line that connects the quarks. Quarks are charged particles. We have gluons that we don't comment gluons as part of strong interaction. But gluons only interact with quarks. And we have a line type implies that that particle has interactions with itself. Higgs interact with itself, W boson interact with itself, gluons interact with itself, and D bosons interact with neutrinos, tau, neutrinos, quarks, boson W. So, for example, Higgs, we see that he only interact with particles that has mass. So we don't have interactions between Higgs and photon because photon is particle. So this is a good scheme to represent all the Lagrangian standard. So here the final part of the lecture. We have a set of problems that standard model don't explain for different motivations. A priori, for example, have a dark matter candidate, and we know that dark matter, so we don't have particles that describe property, homological property particles. Need to extend this standard matter, and we have the neutrino masses. Standard model neutrinos are mass particles, need neutrino mass, plain neutrino. So we need again and the standard. Another problem that is important, we know that in the universe we have more matter that and so we have a difference between violation. So we need to extend the standard model as more interactions that describe violation problems to explain the origin of that problem, matter antimatter symmetry. So the solution is the standard. And one of the solution is, for example, introduce models prime favorite particle. The C prime, for example, is a new particle, very simple, and we can do the same mathematics that we see, and we can create interactions of particles, affect symmetry of this, and we can use colliders find that particle. So this is as lecture. Then the standard model and we can explain some that Z prime, some problems, matter problem, favor changing neutral current, and another problem that we have. So thanks lecture of today.
So do we have any question? We have a question on YouTube from Gabriel. He asked if the Monte Carlo method only calculates the dots in an integral, or if it in any way calculates the area,
The area.
only the area.
The objective is count each one of the points that are inside of
Yeah, because
function.
basically what you're doing is plotting kind of squares, right? And make counting of it and making it smaller, even
Yes.
smaller to have the entire.
Mention is better.
Yeah. That. I hope your question was answered, Gabriel. If not, you can send another message in the group or in the Google Meet or even in the YouTube. Okay. So we have a question here.
Let's see if I get the idea. You plot the point. Point the point.
Related to
You count the points curve.
Mhm.
Divide number of points below the curve by the total number of points,
Mhm.
and it is equal to the area of the curve divided by the area of the square, the big square, right?
equal to the area and
But
you
if
do,
the area of the square is 1, the area of the square 1.
the area is basically the area of the
Because
square equal to the total numbers, right?
yes,
To use a large random numbers.
but if you divide the number of particles below the curve and all the curve, you don't have units of area. You only have it low units if you have the area under the curve divided by the total area. So
This is similar to the other method, geometrical angles, but in this case, points.
I'm just saying that either the area of total area of the points that you the area below the curve.
Yeah, a form, but the say of a total number, random numbers, and we only count that are inside of.
Okay.
So let's thank Maurício again. Do you have a question? Sorry, I have another question.
Thanks for the lecture, Dr. Maurício. My question is about the scholar section.
Mhm.
Can you please go back to this? The Higgs boson interacts with itself, right?
Yeah.
I would like to ask if you have already this interaction has already been noticed, like captured by the collider.
This is a problem. Particle boson appear, and so it's very difficult to measure that quartic that was is we have four boson interact, but they decay instantaneously. So this is one of the most things that machines like measure. Is the self interaction?
For sure, the interaction exists. We have some uncertainty about the measure because of as Mario said, we don't have the ability to see the entire interactions. You have some
Yes.
uncertainty, so have kind of a open limit to open physics, new physics, but for interaction. Sure. The Higgs potential, it's kind of well defined. Of course, you can add some stuff, but at this level, for sure you have that interactions. And you have to think that even if you don't measure directly, it will appear in another interactions because almost everything is connected. So if you have a kind of a Higgs, the quark term you affect the way it interacts with the other particles that we call the propagator. So for sure it exists, but we don't measure with a great precision. Do you agree? Other question? The last one because we are kind of late.
It's about the same topic. But if you confirm, they only measure the interactions between the Higgs, for example, and the most heavier quarks. And the quarks below with less mass, they didn't measure those masses, but assume that this is proportional to the mass. Is that right?
Yes, the one is example. That is really one sec. For example, that term quarks. Quarks are not particles. So exists a research inside of particle physics that we can. So better technique is to measure that interactions. We can measure the mass indirectly of the up quark. Only use mesons that are made of types of quarks. So it's some difficult.
And actually, you can kind of see the interaction between the quarks and the Higgs because of the mass of the Higgs. When you go to loop corrections, the quarks contribute to the correction of the Higgs mass. So if you measure the Higgs mass as it is due to the corrections with interactions with quarks. The most relative one, the most significant one, sorry, it's the top, of course, top quark. So even when you're kind of doing some beyond standard models, constructions, you sometimes just consider the corrections to the top because it's the most significant one. Yeah, but if not the interaction itself, but if you have a correction to the mass, it's a kind of a way to see the interaction. So next, thanks Maurício again, please. Thanks, Maurício. And now we are going to the